the segment is we need to take a little more time to actually talk about those different laws of thermodynamics that kind of dictate some of the stuff that we've already been kind of establishing and working with. So we need to start with the zeroth law. Now, the zeroth law, I don't know why they call it the zeroth law. I'm guessing because they had the first, second, and third law and then said, hey, wait a minute, we probably should talk about this. And it's even more fundamental than the first, second, and third, so let's call it the zeroth law. I don't really know. Anyway, this is just your basic idea behind thermodynamics and what it means to be in equilibrium with each other. Okay, so if you're thermal equilibrium, that means you have equal temperature. Now keep in mind, it doesn't mean equal heat or equal amounts of energy. It just means thermal equilibrium is equal temperature. Okay, so you can have three blocks, A, B, and C. And if A and C are in thermal equilibrium with each other, and B and C are in thermal equilibrium with each other, then by definition, B and A should also be in thermal equilibrium with each other. Okay, so that's our basic idea behind the zeroth law. Is essentially saying that if you have things that are the same in terms of temperatures, you can relate that across multiple objects in series. Okay, so that's our zeroth law. Now that helps us out, but it doesn't really tell us much about how do you get them to be at thermal equilibrium. Okay. So we want to talk about the first law of thermodynamics and kind of get this idea of, okay, what's it mean in terms of two different things being in the same system together, okay? So our first law of thermodynamics, we're basically talking about that in any isolated closed system, energy gained by a substance must equal the energy lost by another, okay? So if you put two things in the same closed system and they're not at thermal equilibrium, one of them will gain some energy and the other one will lose some energy. The amount that one gains must be equal to the amount the other one loses. So we say that the energy that one gains equals the energy that the other one loses, technically. Okay. The difference here is we need to make sure that we keep track of our signs. So if you're gaining energy, that's a positive value. If you're losing energy, that's a negative. A positive cannot equal a negative, so you put a negative with another negative, and now this becomes positive. Okay. Now, conceptually, that might be kind of hard to imagine, but it works out much better when we start applying numbers to this kind of idea. Okay, just kind of imagine this has got to be positive, this has got to be negative, so they can't equal because a positive and negative can't be equal to each other. So by adding a negative sign in to this, we now make both sides positive, and now they can be mathematically equal. Okay, so that's basically what the first law is telling us, is that we can actually track energy from one thing to give us information about the other. Okay. As we kind of move forward. Now, our second law of thermodynamics has multiple parts to it, and we're going to focus on only one of those parts, okay, heat flow. So how does heat actually flow within a system is essentially what we're working with here in this part. So we're actually going to redo this animation here so we can see it again. So essentially, as heat flows, if you take something that's high temperature touching something that's low temperature, heat always flows from high to low. Okay, so the movement of heat energy goes from high energy down to low energy, which that kind of makes sense. And they'll keep changing heat until they become thermal equilibrium with each other. All right. This law is helpful for us because we don't actually have something called cold. Okay, cold doesn't really exist. There's heat and there's the absence of heat. So cold really isn't its own entity, whereas heat is actually a measurable amount of energy. So when you put two things together, one of them has energy, one of them is missing the energy. The one that's missing energy we say is cold. So then the one with more energy will actually distribute its energy in. Very much like the idea of diffusion or effusion that we talked about in previous units. Okay. So our second law then talks about that you're going to have heat flowing together. Okay. So if you put all these concepts together, essentially we're saying that if you're at thermal equilibrium with something, you need to be the same temperature. We're saying that if something loses energy, the other substance has to gain it. And then we're saying that the movement always is from hot to cold in terms of our energies. You put those three concepts together, those three laws together, and we end up getting this kind of relationship. So if we take MCAT, or MC delta T, and we take our delta H, or our enthalpy change from a thermochemical equation, okay? So if we combine this and this together now, applying those principles, we can say that using these three laws, that we can justify that in any chemical reaction, the energy lost or gained could be tracked by a change in temperature of the system, okay? So if we actually physically mix some things together, two solutions, let's say, or a solid into a solution, usually it's done in solution so you can actually measure the temperature of the solution. If you mix those things together, the temperature change of that system will then give you the energy change that came from the reaction. Okay, so if the reaction is releasing energy, it will warm up the system. If the reaction is actually absorbing energy, it'll cool down the system. So we actually can track the energy change by the temperature change within that system. Okay, now we need MCAT for temperature change, and we need delta H for the energy of the reaction. So we can actually set them equal to each other based off of that first law of thermodynamics. So the energy gained by the system must be coming from the energy lost by the reaction. Or the energy gained by the reaction must be coming from the energy lost by the system. It doesn't matter which way you do it, the equation holds. Okay, we have again our negative sign to keep this thing all equal. So if we rearrange that, we can say that the delta H, okay, or the enthalpy of the reaction, okay, or heat of our reaction will equal to the negative energy change we see based off the temperature. Now Q itself is not that useful for us because we don't usually measure Q directly, we measure temperatures. So instead we're going to rewrite this and say that the enthalpy change of our reaction can equal the mass of whatever our solution is times the specific heat capacity of that solution times the change in temperature of that solution. Okay, so we can apply MCAT to delta H and set them equal to each other. Now keep in mind, we do need to make this side negative. Okay, that's going to allow us to set it equal to each other, and our signs will all line up then when we do that. All right. Okay, now that we know this relationship, we can start applying it to kind of these mathematical relationships between heat of reaction and changes in temperature. So to do that, we're going to go back to some practice problems, and we're actually going to tackle these tomorrow in class. We're not going to do them now. So we come back tomorrow, we'll be ready to basically apply that. The first one up here, though, we'll take a look at it real quick. This is something we solved earlier in the unit where we talked about how much energy is released if you have so many grams of magnesium is burnt in an excess of oxygen. Okay, so because of that, we now know the energy is released in this reaction, and we need that to do the second two problems down here as we move forward. Okay, so we're going to end the video here, and we'll start tomorrow with these practice problems. Thank you.